In mathematics and abstract algebra, group theory studies the algebraic structures known as groups. The concept of a group is central to abstract algebra. Other well-known algebraic structures, such as rings, fields, and vector spaces, can all be seen as groups endowed with additional operations and axioms. Groups recur throughout mathematics, and the methods of group theory have influenced many parts of algebra. Linear algebraic groups and Lie groups are two branches of group theory that have experienced advances and have become subject areas in their own right. Various physical systems, such as crystals and the hydrogen atom, can be modeled by symmetry groups. Thus group theory and the closely related representation theory have many important applications in physics, chemistry, and materials science. Group theory is also central to public key cryptography. One of the most important mathematical achievements of the 20th century was the collaborative effort, taking up more than 10,000 journal pages and mostly published between 1960 and 1980, that culminated in a complete classification of finite simple groups. History. Group theory has three main historical sources: number theory, the theory of algebraic equations, and geometry. The number-theoretic strand was begun by Leonhard Euler, and developed by Gauss's work on modular arithmetic and additive and multiplicative groups related to quadratic fields. Early results about permutation groups were obtained by Lagrange, Ruffini, and Abel in their quest for general solutions of polynomial equations of high degree. A Permelvarist Gaulois coined the term group, and established a connection, now known as Gaulois theory, between the nascent theory of groups and field theory. In geometry, groups first became important in projective geometry and, later, non-Euclidean geometry. Felix Klein's Erlangen program proclaimed group theory to be the organizing principle of geometry. Gaulois, in the 1830s, was the first to employ groups to determine the solvability of polynomial equations. Arthur Cayley and Augustin Louis Cauchy pushed these investigations further by creating the theory of permutation groups. The second historical source for groups stems from geometrical situations. In an attempt to come to grips with possible geometries using group theory, Felix Klein initiated the Erlangen program. Sophus Lie, in 1884, started using groups attached to analytic problems. Thirdly, groups were, at first implicitly and later explicitly, used in algebraic number theory. The different scope of these early sources resulted in different notions of groups. The theory of groups was unified starting around 1880. Since then, the impact of group theory has been ever-growing, giving rise to the birth of abstract algebra in the early 20th century, representation theory, and many more influential spin-off domains. The classification of finite simple groups is a vast body of work from the mid-20th century, classifying all the finite simple groups. Main classes of groups. The range of groups being considered has gradually expanded from finite permutation groups and special examples of matrix groups to abstract groups that may be specified through a presentation by generators and relations. Permutation groups. The first class of groups to undergo a systematic study was permutation groups. Given any set X and a collection G of bijections of X into itself that is closed under compositions and inverses, G is a group acting on X. If X consists of n elements and G consists of all permutations, G is the symmetric group Sn. In general, any permutation group G is a subgroup of the symmetric group of X. An early construction due to Cayley exhibited any group as a permutation group, acting on itself by means of the left regular representation. In many cases, the structure of a permutation group can be studied using the properties of its action on the corresponding set. For example, in this way one proves that for n permil 5n, the alternating group N is simple, that is does not admit any proper normal subgroups. This fact plays a key role in the impossibility of solving a general algebraic equation of degree n permil 5n in radicals. Matrix groups. Your next important class of groups is given by matrix groups, or linear groups. Here G is a set consisting of invertible matrices of given order n over a field K that is closed under the products and inverses. Such a group acts on the n-dimensional vector space Kn by linear transformations. This action makes matrix groups conceptually similar to permutation groups, and the geometry of the action may be usefully exploited to establish properties of the group G. Transformation groups, permutation groups and matrix groups are special cases of transformation groups, groups that act on a certain space X preserving its inherent structure. In the case of permutation groups, X is a set. For matrix groups, X is a vector space. The concept of a transformation group is closely related with the concept of a symmetry group. Transformation groups frequently consist of all transformations that preserve a certain structure. The theory of transformation groups forms a bridge connecting group theory with differential geometry. A long line of research, originating with Lie and Klein, considers group actions on manifolds by homeomorphisms or diffeomorphisms. The groups themselves may be discrete or continuous. Abstract groups. Most groups considered in the first stage of the development of group theory were concrete, having been realized through numbers, permutations, or matrices. It was not until the late 19th century that the idea of an abstract group as a set with operations satisfying a certain system of axioms began to take hold. A typical way of specifying an abstract group is through a presentation by generators and relations. A significant source of abstract groups is given by the construction of a factor group, or quotient group, GH, of a group G by a normal subgroup H. Class groups of algebraic number fields were among the earliest examples of factor groups, of much interest in number theory. If a group G is a permutation group on a set X, the factor group GH is no longer acting on X. But the idea of an abstract group permits one not to worry about this discrepancy. The change of perspective from concrete to abstract groups makes it natural to consider properties of groups that are independent of a particular realization, or in modern language, invariant under isomorphism, as well as the classes of group with a given such property, finite groups, periodic groups, simple groups, solvable groups, and so on. Rather than exploring properties of an individual group, one seeks to establish results that apply to a whole class of groups. The new paradigm was of paramount importance for the development of mathematics. It foreshadowed the creation of abstract algebra in the works of Hilbert, Emil Artin, Emmy Noether, and mathematicians of their school. Topological and algebraic groups. An important elaboration of the concept of a group occurs if G is endowed with additional structure, notably, of a topological space, differentiable manifold, or algebraic variety. If the group operations M and I are compatible with the structure, that is are continuous, smooth or regular maps, then G becomes a topological group, a Lie group, or an algebraic group. The presence of extra structure relates these types of groups with other mathematical disciplines and means that more tools are available in their study. Topological groups form a natural domain for abstract harmonic analysis, whereas Lie groups are the mainstays of differential geometry and unitary representation theory. Certain classification questions that cannot be solved in general can be approached and resolved for special subclasses of groups. Thus, compact connected Lie groups have been completely classified. There is a fruitful relation between infinite abstract groups and topological groups. Whenever a group I can be realized as a lattice in a topological group G, the geometry and analysis pertaining to G yield important results about I. A comparatively recent trend in the theory of finite groups exploits their connections with compact topological groups. For example, a single p-adic analytic group G has a family of quotients which are finite p groups of various orders, and properties of G translate into the properties of its finite quotients. Combinatorial and geometric group theory. Groups can be described in different ways. Finite groups can be described by writing down the group table consisting of all possible multiplications Ga H. A more compact way of defining a group is by generators and relations, also called the presentation of a group. Given any set F of generators GIII, the free group generated by F subjects onto the group G. The kernel of this map is called subgroup of relations, generated by some subset D. The presentation is usually denoted by a FDA euro. For example, The group Z equals a euro A. A euro can be generated by one element A and no relations, because NA1 never equals 0 unless n is 0. A string consisting of generator symbols and their inverses is called a word. Combinatorial group theory studies groups from the perspective of generators and relations. It is particularly useful where finiteness assumptions are satisfied, for example finitely generated groups, or finitely presented groups. The area makes use of the connection of graphs via their fundamental groups. For example, one can show that every subgroup of a free group is free. There are several natural questions arising from giving a group by its presentation. The word problem asks whether two words are effectively the same group element. By relating the problem to Turing machines, one can show that there is in general no algorithm solving this task. Another, generally harder, algorithmically insoluble problem is the group isomorphism problem, which asks whether two groups given by different presentations are actually isomorphic. For example, the additive group Z of integers can also be presented by a euro x, y x equals a euro. It may not be obvious that these groups are isomorphic. Geometric group theory attacks these problems from a geometric viewpoint either by viewing groups as geometric objects, or by finding suitable geometric objects a group acts on. The first idea is made precise by means of the Cayley graph, whose vertices correspond to group elements and edges correspond to right multiplication in the group. Given two elements, one constructs the word metric given by the length of the minimal path between the elements. A theorem of Milnor and Svark then says that given a group G acting in a reasonable manner on a metric space X, for example a compact manifold, then G is quasi-isometric to the space X, representation of groups, saying that a group G acts on a set X means that every element defines a bijective map on a set in a way compatible with the group structure. When X has more structure, it is useful to restrict this notion further. A representation of G on a vector space V is a group homomorphism, i.e. G a GL, V, where GL, V, consists of the invertible linear transformations of V. In other words, to every group element G is assigned an automorphism I, G, such that I, G, AI, H, equals I, G H, for any H and G. This definition can be understood in two directions, both of which give rise to whole new domains of mathematics. On the one hand, it may yield new information about the group G. Often, the group operation in G is abstractly given, but via I, it corresponds to the multiplication of matrices, which is very explicit. On the other hand, given a well-understood group acting on a complicated object, this simplifies the study of the object in question. For example, if G is finite, it is known that V above decomposes into irreducible parts. These parts in turn are much more easily manageable than the whole V. Given a group G, representation theory then asks what representations of G exist. There are several settings, and the employed methods and obtained results are rather different in every case. Representation theory of finite groups and representations of Lie groups are two main subdomains of the theory. The totality of representations is governed by the group's characters. For example, Fourier polynomials can be interpreted as the characters of U1, the group of complex numbers of absolute value 1, acting on the L2 space of periodic functions. Connection of groups and symmetry. Given a structured object X of any sort, a symmetry is a mapping of the object onto itself which preserves the structure. This occurs in many cases. For example, if X is a set with no additional structure, a symmetry is a bijective map from the set to itself, giving rise to permutation groups. If the object X is a set of points in the plane with its metric structure or any other metric space, a symmetry is a bijection of the set to itself which preserves the distance between each pair of points. The corresponding group is called isometry group of X. If instead angles are preserved, one speaks of conformal maps. Conformal maps give rise to Kleinian groups, for example. Symmetries are not restricted to geometrical objects, but include algebraic objects as well. For instance, the equation has the two solutions, and in this case, The group that exchanges the two roots is the Gaulois group belonging to the equation. Every polynomial equation in one variable has a Gaulois group, that is a certain permutation group on its roots. The axioms of a group formalize the essential aspects of symmetry. Symmetries form a group. They are closed because if you take a symmetry of an object, and then apply another symmetry, the result will still be a symmetry. The identity keeping the object fixed is always a symmetry of an object. Existence of inverses is guaranteed by undoing the symmetry, and the associativity comes from the fact that symmetries are functions on a space, and composition of functions are associative. Frucht's theorem says that every group is the symmetry group of some graph. So every abstract group is actually the symmetries of some explicit object. The saying of preserving the structure of an object can be made precise by working in a category. Maps preserving the structure are then the morphisms, and the symmetry group is the automorphism group of the object in question. Applications of group theory abound. Almost all structures in abstract algebra are special cases of groups. Rings, for example, can be viewed as abelian groups together with a second operation. Therefore group-theoretic arguments underlie large parts of the theory of those entities. Gaulois theory uses groups to describe the symmetries of the roots of a polynomial. The fundamental theorem of Gaulois theory provides a link between algebraic field extensions and group theory. It gives an effective criterion for the solvability of polynomial equations in terms of the solvability of the corresponding Gaulois group. For example, S5, the symmetric group in 5 elements, is not solvable, which implies that the general quintic equation cannot be solved by radicals in the way equations of lower degree can. The theory, being one of the historical roots of group theory, is still fruitfully applied to yield new results in areas such as class field theory. Algebraic topology is another domain which prominently associates groups to the objects the theory is interested in. There, groups are used to describe certain invariants of topological spaces. They are called invariants, because they are defined in such a way that they do not change if the space is subjected to some deformation. For example, the fundamental group counts, how many paths in the space are essentially different. The Poincaré copyright conjecture, proved in 2002/2003 by Grigory Perelman, is a prominent application of this idea. The influence is not unidirectional, though. For example, algebraic topology makes use of Eilenberg-Euro-MacLane spaces, which are spaces with prescribed homotopy groups. Similarly, algebraic K-theory stakes in a crucial way on classifying spaces of groups. Finally, the name of the torsion subgroup of an infinite group shows the legacy of topology in group theory. Algebraic geometry and cryptography likewise uses group theory in many ways. Abelian varieties have been introduced above. The presence of the group operation yields additional information which makes these varieties particularly accessible. They also often serve as a test for new conjectures. The one-dimensional case, namely elliptic curves, is studied in particular detail. They are both theoretically and practically intriguing. Very large groups of prime order constructed in elliptic curve cryptography serve for public key cryptography. Cryptographical methods of this kind benefit from the flexibility of the geometric objects, hence their group structures, together with the complicated structure of these groups, which make the discrete logarithm very hard to calculate. One of the earliest encryption protocols, Caesar's cipher, may also be interpreted as a group operation. In another direction, toric varieties are algebraic varieties acted on by a torus. Toroidal embeddings have recently led to advances in algebraic geometry, in particular resolution of singularities. Algebraic number theory is a special case of group theory, thereby following the rules of the latter. For example, Euler's product formula captures the fact that any integer decomposes in a unique way into primes. The failure of this statement for more general rings gives rise to class groups and regular primes, which feature in Comma's treatment of Fermat's last theorem. The concept of the Lie group is important in the study of differential equations and manifolds. They describe the symmetries of continuous geometric and analytical structures. Analysis on these and other groups is called harmonic analysis. Har measures, that is integrals invariant under the translation in a Lie group, are used for pattern recognition and other image processing techniques. In combinatorics, the notion of permutation group and the concept of group action are often used to simplify the counting of a set of objects. See in particular Burnside's lemma. The presence of the 12 periodicity in the circle of fifths yields applications of elementary group theory and musical set theory. In physics, groups are important because they describe the symmetries which the laws of physics seem to obey. According to Noether's theorem, every continuous symmetry of a physical system corresponds to a conservation law of the system. Physicists are very interested in group representations, especially of Lie groups, since these representations often point the way to the possible physical theories. Examples of the use of groups in physics include the Standard Model, gauge theory, the Lorentz group, and the Poincaré copyright group. In chemistry and materials science, groups are used to classify crystal structures, regular polyhedra, and the symmetries of molecules. The assigned point groups can then be used to determine physical properties, spectroscopic properties, and to construct molecular orbitals. See also, group, glossary of group theory, list of group theory topics, notes, Ilwes, Richard, An Enormous Theorem, The Classification of Finite Simple Groups, PLOS Magazine, Issue 41, December 2006. This process of imposing extra structure has been formalized through the notion of a group object in a suitable category. Thus Lie groups are group objects in the category of differentiable manifolds and affine algebraic groups are group objects in the category of affine algebraic varieties. Schopp and Linden 2001, writing Z equals XY, 1 has G equals a euro Z, YZ3 equals Y euro equals a euro ZAR euro. La Harpe 2000, such as group cohomology or equivariant K-theory. In particular, if the representation is faithful. For example the Hodge conjecture. See the Birch-Swinnerton-Dyer conjecture, one of the Millennium Problems, Abramovich, Dan. Karu, Call. Matsuki, Kenji. Lodarczyk, Jaroslaw, Torification and Factorization of Birational Maps, Journal of the American Mathematical Society 15, 531 a 572, doi, 10.1090 per second 0894-0347-02-00396X, MRA 1896232 Lenz, Rayner, Group Theoretical Methods in Image Processing, Lecture Notes in Computer Science 413, Berlin, New York, Springer Verlag, doi, 10.1007/3-540. -52290-5, ISBN A978-0-387-52290-6. References, Borel, Armand, Linear Algebraic Groups, Graduate Texts in Mathematics 126, Berlin, New York, Springer Verlag, ISBN A978-0-387-97370-8, MRA 1102012. Carter, Nathan C., Visual Group Theory, Classroom Resource Materials Series, Mathematical Association of America, ISBN A978- 0-88385-757-1, MRA 2504193. Cannon, John J., Computers and Group Theory, A Survey, Communications of the Association for Computing Machinery 12, 3 doi, 10.1145/362,835.36287, MRO 290613. Frucht, R., Herstellung von Graphen mit Vegetabiner Abstraktegruppe, Compositio Mathematica 6, 239 €. 50, ISNA 0010-437 Zan, Golubitsky, Martin. Stewart, Ian, Nonlinear Dynamics of Networks, The Gruppoid Formalism, Bull. Amma. Math. SOC 43, 305 €364, doi, 10.1090 per second 0273-0979-06-01108-6, MRA 2,223,010 showed the advantage of generalizing from group to groupoid. Judson, Thomas W., Abstract Algebra, Theory and Applications. An introductory undergraduate text in the spirit of texts by Gallian or Herstein, covering groups, rings, integral domains, fields and Galois theory. Free downloadable PDF with open source GFDL license. Kleiner, Israel, The Evolution of Group Theory, A Brief Survey, Mathematics Magazine 59, 195 €215, doi, 10.2307/2690312, ISNA 0025-570X, JSTORA 2690312. MRA 863,090. La Harpe, Pierre de, Topics in Geometric Group Theory, University of Chicago Press, ISBN A978-0-226-31721. -2. Livio, M., The Equation That Couldn't Be Solved, How Mathematical Genius Discovered the Language of Symmetry, Simon & Schuster, ISBN A0-7432-5820-7. conveys the practical value of group theory by explaining how it points to symmetries in physics and other sciences. Mumford, David, Abelian Varieties, Oxford University Press, ISBN A978-0-19-560528-0, OCLCA 138290. Ronan M., 2006. Symmetry and the Monster. Oxford University Press. ISBN 0-19-280722-6. For lay readers. Describes the quest to find the basic building blocks for finite groups. Rotman, Joseph, An Introduction to the Theory of Groups, New York, Springer Verlag, ISBN A0-387-94285-8. A Standard Contemporary Reference. Sharp, Paul E. Linden, Roger C., Combinatorial Group Theory, Berlin, New York, Springer Verlag, ISBN A978-3-540-41158-1. Scott, W. R. 1964, Group Theory, New York, Dover, ISBN A0-486-65377-3. A inexpensive and fairly readable, but somewhat dated in emphasis, style, and notation. Schatz, Stephen S., Profinet Groups, Arithmetic, and Geometry, Princeton University Press, ISBN A978-0-691-08017-8, MRA 0347778. Weibull, Charles A., An Introduction to Homological Algebra, Cambridge Studies in Advanced Mathematics 38, Cambridge University Press, ISBN A978-0-521-55987-4, OCLCA 36131259, MRA 1269324. External links, History of the Abstract Group Concept, Higher Dimensional Group Theory. This presents a view of group theory as level 1 of a theory which extends in all dimensions, and has applications in homotopy theory and to higher dimensional non-abelian methods for local to global problems. Plus Teacher and Student Package, Group Theory. This package brings together all the articles on group theory from PLUS, the online mathematics magazine produced by the Millennium Mathematics Project at the University of Cambridge, exploring applications and recent breakthroughs, and giving explicit definitions and examples of groups. U.S. Naval Academy Group Theory Guide. A general introduction to group theory with exercises written by Tony Gaglian.